This is an overview of the Linear Temporal Logic, or LTL, based monitor for smart manufacturing systems. A quick summary. The LTL based monitor checks for continuous wear of actuators and discrete errors in the work cell. It employs underlying concepts from previous work and demonstrates them on an industry-inspired use case, which we will present here in a second. It uses the following computer tools for proof of concept: VREP, which is a 3D simulation environment, and MATLAB. And it drives towards future work, which develops adaptive, intelligent control strategies to evenly spread out wear for extending asset life. So here is the VREP environment. We're going to call this first robot Ben and the second robot Mike. Boxes will enter the work cell on this first conveyor. Ben performs a pick and place operation, puts them on the second conveyor, and robot Mike performs the drilling operation. Boxes then flow out from that second conveyor to leave the work cell. In this section, we will discuss the mathematical concepts involved. First, we have the robot Mike's transition system representation. Mike is, again, performing a drilling action on the boxes. The circles represent the mode or state of the robot, and the arrows show the transitions between those states. We use the term motion primitive for these transitions. The states have labels associated with them, which represent the properties of the specific states. These labels can also be called propositions. For example, circle number 4 has the label of M_drill, which means that Mike performs the drilling action in this state. Similarly, this is the transition system representation of the picking and placing robot, Ben. As it appears from the diagram, this robot has some added degree of complexity in its movement as compared to Mike. This mathematical representation can be propagated easily to show a system having the above two robots as subsystems. Here we perform a product of the two transition systems to get a more complicated transition system structure which shows all the possible behaviors of a robot with respect to the other one. In the next few slides, we will see how the work cell transition system can be tailored according to particular objectives. Here we have, for example, a work cell objective stating Mike should be in initial position when Ben is holding the box. This objective can be converted to a linear temporal logic, or LTL, statement by using the labels. Now, to use it for tailoring the operation, we need to convert it to a transition system-like structure. This can be done by using the LTL to Buki automaton tool. And what we're seeing is what we get after conversion to a Buki automaton. To create the complete work cell transition system, we can take an automaton product between these two to get the work cell transition system that follows the objective we described. In this section, we'll look at the contents of the MATLAB display screen. The screen has two main sections. The first one, that we call a continuous information section, logs the continuously changing data from the work cell. These include the wear of the 6 joints in each robot and the task completion time of the 2 robots. The second section records the discrete information from the work cell. This information includes the motion primitives of the two robots. A certain circle is lit to indicate the motion primitive Ben or Mike is in. Discrete information also indicates the discrete objective that we discussed in the last section. And at the bottom part of the display is the overall status. This shows if the work cell is satisfying or violating the discrete objective. Now we will demonstrate the simulator in action. In the VREP window, we can see the two robots performing their task. In the little window in the upper left corner, however, we have the MATLAB display screen showing the corresponding information. Taking a closer look at the MATLAB interface, we can see how where of all the joints are being updated in real time. It can also be observed that since Ben is performing a job involving motion along multiple degrees of freedom, wear incurred over time is greater for Ben as compared to Mike. Now let's introduce the alternate strategies we have designed for Ben so that in case of a breakdown, Ben may shift to other strategies with lesser wear and ultimately cost. The video shows two ways of grabbing and placing the box. In the future, we want to incorporate the alternative strategies in the movement plan automatically. We want to update the simulation such that for a particular level of wear in the work cell, we adopt a specific alternative strategy.